Today we will present the Project Lab BL2612. So this is the figure 1 calculation for theory. So for this theory we assume the beta is equal to 120. So we use the approximate method to determine the VB, VE, IE and VC. So here we know that the VB is equal to VTH, and we can find the VTH. So for VB the value is 2.3256 volt, and then we can find the VE, which is 1.6256 volt, and also can find the IE, which is also the value is 1.6256 milliampere. So since we have all the value, we can find the VC, which is the value of VC is 5.1 volt. And then to find the AV, we need to find the ZI first, and then R in is equal to RE plus RE over beta plus 1. So for RE we already calculate, which is 15.9941 ohm. And then we get the value for R in, which is 24.2586 ohm. And then we can continue to find the ZI. So we get the value of ZI, which is 2110.4891 ohm. And then Z0 is equal to RC, which is 300 ohm. So we can find the voltage gain, which is AV, is equal to negative beta IBRC divided by IB beta R in. And then after we cancel out, we get the negative RC over R in, and then the value of AV is negative 123.6675. And then we can find the value of V out, since we have the V in. So the value for V out is 6.1834 volt. So for the figure 2 calculation theory, we also do the same method, which is approximate method, to determine the VB, VE, IE and VC. So here even we use the same method, they are different in to find the AV, because for this figure 2 the emitter is bypass. So there are different formula we use to get the AV. So to find the AV, negative beta IBRC divided by IB beta RE plus RE. So we cancel out, we can get the negative RE over RE plus RE. So the AV is negative 0.9843. So we can find the value of V out. So V out is 0.9843 volt.
This section presents the multi-sim simulation result used to verify the theoretical analysis of the BJT amplifier circuit. As you can see here, function generator I've been set to 1 kilohertz frequency and 0.5 because the question is asked for 1 volt, so it is using peak to peak. So we divide by 2 and it gets 0.5. And then you can start and run, but before this you need to find the VC, VB, VE and IE, and also V out. The red color is V in and the blue wire is V out. Then you can tap to the oscilloscope and then you can run it and pause to get the waveform. As you can see, the scale is same. As you can see in the result, we already get the VC, VB and VE and also IE, V out and V in. The red waveform represents the input voltage V in connected to channel A, while the blue waveform represents the output voltage V out connected to channel B. Both channels use the same time scale of 500 microseconds per division, which show that the input and output signal have the same frequency. Next, we move to figure 2. Next, we need to find the VC, VB, VE, IE, and also the same V in and V out. And then we apply the same thing, 1 kilohertz frequency and 0.25 V peak to peak. And then you need to run the simulation and tap the oscilloscope to get the waveform. As a result, the figure 2 multisim, we already get the VC, VB and VE and also IE, V out and also V in. In the oscilloscope waveform for the figure 2, the red trace represents the input voltage V in, which is connected to channel A, while the blue trace represents the output voltage V out, which is connected to channel B. Channel A use a smaller voltage scale because the input signal amplitude is very small in the millivolt range. This allows the V in waveform to be displayed clearly without appearing flat. Channel B use a larger voltage scale because the output voltage is significantly higher. In the volt range, using a larger scale prevents the output waveform from being clipped on the display. Even though the two signals have different voltage scale, but waveform can be observed clearly on the same time axis. This make it easier to compare the amplitude difference and phase inversion between V in and V out. From the waveform, it can be seen that the output signal is amplified and inverted relative to the input signal.
So this is the table of comparison, the theory versus the software multisim. So here we compare the value of VC, VB, VE, IE, V in peak to peak, V out peak to peak, and AV. So here we have the question gave us the two figure 1 and figure 2. So for figure 1, so basically the theory and software, they have different value. Since the theory, we need to follow the theory value, but in the software, the value need to be close to the theory value. So in our software multisim, we get all close to the theory value from the VC until the AV. And then of course for this project, they have a little bit error in comparing the theory value with the software.